In this experiment, we will be determining the molar mass of a volatile liquid using its vapor pressure and the ideal gas law. The objective of this experiment is to determine the molar mass of an unknown volatile liquid. To accomplish this, we will vaporize the liquid in a flask. The ideal gas law will be used to calculate the number of moles of vapor in the flask. All molecules experience intermolecular forces. These forces are non-bonding and act between molecules to either attract or repel other molecules. The strength of intermolecular forces depend on the type. Recall that there are three common intermolecular forces. First, we have dispersion forces. These are the weakest intermolecular forces, and they are present between all molecule pairs. Secondly, we have dipole-dipole forces. These are stronger than dispersion forces in general, but only occur between molecules with permanent dipole moments. This requires an electronegative atom bonded to a non-electronegative atom, generating a small magnet in the molecule. Lastly, we have hydrogen bonding. This is the strongest type. Hydrogen bonding is a special case of dipole-dipole forces. This requires a hydrogen being bonded to either nitrogen, oxygen, or fluorine. The stronger the intermolecular forces, the greater attraction molecules feel toward one another. This is the primary reason for the three common states of matter. The second factor is the kinetic energy of the molecules. The balance between the kinetic energy and the strength of the intermolecular forces will determine the state of matter. In gases, the kinetic energy is so great that intermolecular forces are negligible, and the particles do not interact. In general, they do not even know other particles exist. In solids, the kinetic energy is so low, the strength of the intermolecular forces hold the molecules very close together, not allowing them to move very much at all. In the liquid phase, the kinetic energy is at a moderate level. It's neither too high nor too low. This means that the intermolecular forces are approximately the same magnitude as the kinetic energy. Because of this, liquid molecules are held fairly strongly together, but are free to move away from one another to some extent. This results in liquids having a very important property known as the vapor pressure. Let's start by considering an empty flask. We can then introduce a small amount of liquid into the bottom of the flask and seal it up. At the surface of the liquid, a few molecules will have enough kinetic energy to escape from the liquid and to jump up into the atmosphere above it. Early on, the number of molecules escaping is very small. As more and more molecules enter the atmosphere, a few of them begin to strike the liquid surface. These will lose kinetic energy and become stuck in the liquid again, or recondense. At this point, the number of molecules escaping is much greater than the number of molecules re-entering the liquid. As time progresses, the number of molecules escaping slows down, and the number of molecules re-entering the liquid increases, but also begins to slow down. Eventually, for every molecule that escapes, one re-enters. This is a state of equilibrium, where the total number of molecules in the atmosphere stays constant. This now equilibrated vapor above the liquid generates a pressure inside the flask. This pressure will depend on the identity of the liquid and the temperature. This pressure is the vapor pressure of the liquid. All liquids have a vapor pressure, but some liquids have a much higher vapor pressure than others, meaning that the number of molecules in the atmosphere above the liquid is very large. A liquid such as gasoline has a high vapor pressure. We know this because we can smell the gasoline very easily if a small amount of it is around. Liquids with a high vapor pressure are called volatile liquids. Low vapor pressure liquids are called non-volatile. The more volatile a liquid, the weaker the intermolecular forces. These weaker forces make it easier for the liquid molecules to escape and therefore generate a high vapor pressure. The goal of this experiment is to determine the molar mass of an unknown volatile liquid. By definition, the molar mass of a compound, capital M, is the ratio of the mass of the compound, lowercase m, to the corresponding number of moles, lowercase n. Or mathematically, the molar mass is equal to the mass divided by the number of moles. The mass is easy to measure. We simply weigh a given volume of the liquid. Determining the moles of liquid present is a bit more tricky. We will utilize the vapor pressure of the liquid to do this, but we need a relationship between the number of moles of vapor and other physical properties. The vapor above a liquid will obey a gas law, which relates the temperature, pressure, and volume. The simplest of these gas laws is known as the ideal gas law. The ideal gas law assumes that the vapor molecules do not exert forces on one another and don't even know other gas molecules are present. The ideal gas law has the following mathematical form: PV equals nRT, where P is the pressure of the gas, V is the volume of the gas, N is the number of moles of gas, and T is the absolute temperature, meaning the temperature in Kelvin. The proportionality constant R depends on the units that are used. The most common value is 0.08206 liter atmosphere per mole Kelvin. At this point, we have all the pieces we need, so let's put them together. What information do we need, first of all? Well, to calculate the molar mass, we need 1, the mass of the liquid, and 2, the moles of liquid. To get the moles of liquid, we will vaporize the liquid in a container of known volume. We can then use the ideal gas law to calculate the number of moles. To do this, we will need the volume of the container, the temperature of the vapor, and the pressure of the vapor. The first step is to determine the volume of the flask. The flask that we will be using is a 125 milliliter Erlenmeyer flask, so it may not seem necessary to determine the actual volume. But remember, this just means that it can safely hold 125 milliliters of liquid. This is not the actual volume of the flask, since there is headspace above the liquid when it's filled to the 125 milliliter line. To measure the total volume, we will fill it completely to the top with water. We will then use a 100 milliliter graduated cylinder to measure the total volume of water contained in the full flask. You will carefully fill the graduated cylinder with the water from the flask until you reach the 100 milliliter mark. At this point, discard this water and then pour the remaining water into the cylinder. Record this volume and add 100 milliliters to it. This is the total volume of the flask. The next step is to dry out the flask and to create a cover for it. The cover will be a square of aluminum foil that's held in place with a rubber band. Next, you will weigh the flask, the foil, and the rubber band together and record this mass in your notebook. Then, using a pipette, transfer about 2 milliliters of the volatile liquid into the flask and cover it. Using a staple, poke a small hole in the foil to allow some of the vapor and the air to escape. The key to accurately determining the number of moles is to completely vaporize the liquid and fill the flask with the vapor. To accomplish this, we will heat the flask in a boiling water bath. After several minutes, the liquid should be completely vaporized. There will be sufficient liquid at the beginning that most of the vapor will exit the hole in the foil and push the air out of the flask along with it. The remaining vapor will be used to calculate the mass and the moles. Since we know that water boils at 373 Kelvin, we also now know the temperature for the ideal gas law. Furthermore, since the gas expanded against the pressure of the atmosphere, we also know that the pressure of the vapor inside the flask must be equal to atmospheric pressure. We will measure this directly using a barometer, giving the pressure for the ideal gas law. At this point, we carefully remove the flask from the water and allow it to cool. As it cools, the vapor will condense back into liquid. The resulting liquid will be considerably less than what we started with. Once the flask is completely cooled to room temperature, we will reweigh it with the condensed liquid and record the new mass in our notebook. We now have obtained all of the information that we need to finish the calculations. Since the condensed liquid all came from the vapor, the mass of the liquid is equal to the mass of the vapor. To obtain the mass of the liquid, we subtract the mass of the empty flask plus the cover from the mass of the flask and the condensed liquid plus the cover. We now have the value for M. The number of moles of vapor are found using the ideal gas law. The numerical values of T, V, and P are the temperature of the boiling water, the total volume of the flask found from using the graduated cylinder, and atmospheric pressure measured with the barometer. We can now calculate the number of moles in using the ideal gas law. The last step is to find the molar mass, and to do this we just divide M by N. We will practice with a known liquid, acetone. Then we will determine the molar mass of the unknown liquid in the same manner. This concludes this introductory lecture. Information regarding the calculations and data analysis will be included in a second video.